Significant figures. Love them or hate them, you still got to know them. And they are especially important in this course. So let's take a look at why they're so important and go over a few examples to refresh your memory for how they work. Let's go. So one of the things that I think confuses students about significant figures is the question, when do you even need to use them? When do they apply? And the key to this question is to realize that the only numbers that can affect significant figures is a measurement. Okay, let me say that again. Measurements are the only numbers that can control significant figures. So what do 99% of measurements have in common? Well, they all have units. Well, not quite all of them. Something like absorbance doesn't have units, but it's still a measurement. So what numbers aren't measurements? So let's say, for example, you need to take an average of three numbers. And I'll just write three numbers down here. So you have, say, 6.00 plus 7.00 plus 8.00. Right, and let's just say these are all liters, just to give them a unit. Okay, and if you were to divide that by a number, that number is 3. Now 3 is not a measurement, right? You're just taking an average of these three numbers. So 3 is not going to control the number of significant figures. The only thing that's going to do that is the top three measurements. So the answer to this is, of course, going to be 7.00 liters, right? We're just making the number simple. Okay, so hopefully that makes something a little bit more clear about when significant figures need to be used, right? So we're only worried about measurements. And in this class, we're going to be taking a lot of measurements and talking about measurements quite a bit. Okay, so here we go. When you measure something, you're certain of some digits and uncertain of others. All right, this is going to become important in lab. So significant figures are going to be the maximum number, the minimum number of digits that you need to express a number without losing its accuracy. Okay, so let's just zoom up on this ruler to get an idea of what I'm talking about. All right, so we'll look at the top scale percent transmittance. And the line, it's a vertical line here showing you what the measurement is. So you know for sure that it's greater than 50. You also know for sure that it's greater than 58, right? But once you get into this little area here, between those two values, now you kind of have to guess. So you're not sure what it is. Is it 58.1, 58.2? Right? You can't say it's 58 because you know it's a little bit more. You can't say it's 59, obviously, because it's definitely less than that. So what you have to do in this case is make an educated guess at what that final value is, right? And that last number, whatever it might be, okay, so let's just make a guess at what this number is. We know it's at least 50 something. We know it's at least 58 something, and we'll guess 58.2. And since it's a measurement, we'll put on a unit, right? So again, we know these two numbers here. Those are certain. You know it's at least 58. The 2, that's your first uncertain digit. Okay, some of you might see it as a 1 if you look at that measurement. Some of you might see it as a 3. Again, there's some uncertainty in that final value. Okay, so when we're taking measurements, you have to sometimes read in between these graduations. And this will be important when you're in lab, doing a titration, for example, and you are reading a burette. You'll come into situations where the meniscus will be between graduations, and you have to make sure that you record where that meniscus is, or at least your best guess as to where that meniscus is between the graduations of the burette. Okay, so this is helping us keep accuracy, right? 58.2 is clearly more accurate than 58. And we can see that just by looking at the measurement itself, or by looking at the line that goes between those two measurements. All right, so let's get to the nitty-gritty of significant figures. So when are zeros important? Zeros are always important if they're in the middle of a number. Okay, so some of the questions that you get is, does this 0 count as a significant figure? I think it's pretty obvious if it's in the middle of a number, right? Like this guy right here. That's going to be significant. Okay, so this first number here, 4.025, we'll give these some units too. We'll call this moles. We'll call them all moles, just for the heck of it. Okay, so that 0 is going to be significant. So this first number has how many significant figures? Hopefully you know that has 4. Okay, the next one has 3 significant figures. All right, here's a 0 that's at the end of a number. Okay, if you're writing that 0 down, you're telling me, or telling whoever's reading that number is a significant digit. Here you go again, 2 more. In this case, you're telling the person looking at that number that those 2 zeros are significant. Okay, so this particular value at the end here has 5 significant figures, right? So this one has 5 significant figures. Okay, the one I think that is sometimes confusing is a number like this guy right here. So these zeros here, those are not significant numbers. Okay, they're not significant zeros because what they're just telling you is the power of 10 that the number is. So if you're ever confused about how many significant figures that are in a number, whether it's this guy here, 9.025 times 10 to the 4, or this one here, write the number in scientific notation, because scientific notation is going to tell you where the significant figures start. Okay, so here it is. This is that same number as above, but written as scientific notation. And if you count the numbers from left to right, you should realize that this has 5 significant figures, which is also the same as this guy up here. So these are the 5 numbers that actually matter. Okay, so you can look at this number also and say, well, you count this way to the right of the decimal place until you hit the first number that isn't a 0, and then you start counting until the end. Okay, so what about this number down here, 92,500? Now the way it's written there, it's ambiguous. We don't know if those last 2 zeros are significant or not. Okay, there's 2 ways to determine, or 2 ways to show that this is significant, those last 2 zeros. First way would be to put a decimal point right at the end of the 0. Okay, that's not as commonly done as the other method that you could do, which would be to write that in scientific notation, which would be the same as the first number at the top, 9.2500 times 10 to the 4. Okay, so that's how you would write that number in scientific notation, and then that would tell you for sure which numbers are significant. In this case, we're going to say they're all significant. Okay, so now significant figures and calculations is going to be something that you will run into a lot in the lab. Not as much with addition and subtraction, although you will have to do addition and subtraction when you take readings from a burette. So during a burette measurement, what you have to do is take an initial reading. It might be, say, 0.05 milliliters, and then take a final reading, say that's 25.68 milliliters, and then you'll have to subtract your initial value from your final reading in order to get the amount of titrant that you have added to your solution. So when you're adding and subtracting, the thing you have to remember is that the number of decimal places in the answer will be the same as the smallest number of decimal places in one of your values. Okay, so if we look at the first example, we can see that we have 3 decimal places in the first number and 3 decimal places in the second number. So that means that the result of that calculation must also have 3 decimal places. Okay, so now let's look at this example on the right. Okay, so it's asking you what is the molar mass of potassium fluoride, or Kf, right? And it's giving you the molar mass of fluorine, which has a lot of significant digits, the molar mass of potassium, which has also a lot of significant digits, but fewer than fluorine. So where is this number going to be cut off? All you have to do is to look at the measurement that has the fewest number of digits after the decimal place. That ends up being the potassium. And then simply cut off your calculation right there, right, in terms of number of significant figures that are needed. So the answer for this, is that going to be down here A, B, C, or D? Right? Which one of those answers is it going to be? Well, we have 4 numbers after the decimal place, and we're going to cut that off at 4 numbers after the decimal place because that's the number of digits after the decimal place in potassium. So the answer for this question is going to have to be B because it also has 4 numbers after the decimal place. So now if we go to multiplication and division, in this case we're not worried about decimal places, but we're worried about the total number of significant figures in each of these measurements. Okay, so in the first example, we have 2 significant digits here, we have 4 significant digits here, and our calculation at the end must have the same number of significant digits as our measurement that has the fewest number of significant figures. So our 2.5 has 2 sig figs, so the 4.5, our answer, must also have 2 significant figures. So the one thing you have to realize here is that the number of decimal places is not necessarily going to be the same in the answer, and that is shown here in the second example. So they both have 2 digits after the decimal place, but when you do the division, it ends up having, or the answer ends up having 3 digits after the decimal place. And that is because this measurement here, which has 4 significant figures, is controlling the value here, is controlling the number of significant figures in this number here, because 39.90 has fewer significant figures than 198.87. So you're always looking at the fewest number of sig figs in one of your measurements to help you determine how many sig figs you should have in your final answer. Now, rounding is fairly simple in most cases, and you're not really going to run into any issues with it except for potentially one situation. And it's a situation that's not going to come up very often. So normal rounding, right? You look at your first uncertain digit, which is going to be your last significant figure. You look beyond that and determine whether or not the values after that are more than halfway to the next number. If they are, you round up. If you don't, you leave it where it's at. Now the problem comes when you have a number that is exactly halfway in between 2 values. So for example, we'll just take these 2 numbers down at the bottom here. So 12.450 and 12.550. All right, so we look beyond the 5, or so we look beyond the 4, we have a 5. Right? We look beyond this 5, we have another 5. Right? So it's exactly halfway in between 2 numbers. So like I said, it's very, very rare for this to actually happen because there's probably going to be other digits after the last 0 in that case. But if you do end up with something like this, the rule is that you're always going to be rounding to the nearest even number. Right? So for the case of 12.450, if you wanted to round that to the nearest tenth or the nearest single decimal place, that's going to end up being 12.4 because that's the nearest even number. And the other example here, say if you're rounding that to the nearest even number, you would round that to 12.6. Now hopefully you can do the first 2 examples because they are below halfway or less than halfway, and this one is above halfway, so this one's going to round up to 5. You only have to worry about rounding to the nearest even number if you have a situation where the numbers afterwards are exactly halfway between the 2 values that you might round to. Okay, like I said, that's not going to happen very often. I don't think it's really ever happened. But just be aware of it. It's to avoid any bias for always rounding up, for example. Okay, so logarithms and pH. So once we get to these chapters and trying to determine pHs and concentrations of H pluses and whatnot, that's when we're going to be worried about using logarithms. Mostly we're using base 10 logarithms. Sometimes I use natural logs, but I don't think we'll be touching that in this course at all. So when you're taking the log of a number, you end up with a number that looks like this over here. Okay, and we have two different parts of that number. We have the mantissa, which is this, the numbers after the decimal place, and then we have the characteristic, which is the blue number there before the decimal place. Now it's important to know the differences between these. Okay, so the 2 is basically just telling you the power of 10. Okay, so if you look at it, that 2 is, sometimes it's the same as that number there. It's not quite always the same, but in a lot of cases it is the same number. So the 530 just tells you, that the 530 refers to this part of the number here. Okay, so when you're taking the log of a number, the value that you're taking the log of is going to control the number of significant figures. So this number has 3 significant figures. Your pH, well actually this is not a pH in this case, but your value is also going to have 3 significant figures. But the question is, what counts as significant figures? Okay, the characteristic does not count as a sig fig. So this 4 here doesn't count. So you're going to be starting from this 4 and counting your significant figures from there. So since there are 3 significant figures in the number that you are taking the log of, the answer should also have 3 significant figures, and these in the mantissa are going to count as their significant figures. So if we get to a situation where we're trying to figure out what the pH is, giving a concentration of H+, okay, so if you remember from previous courses, right, the pH equals the negative log of the concentration of H+. So if we take the negative log of 3.39 times 10 to the minus 5, we're going to get a number like this, 4.4698003. But obviously that's not going to be the pH because it has too many significant figures. Okay, so our value that we're taking the logarithm of, or the negative log of, has 3 significant figures. So our pH should also have 3 significant figures. Right? Those are the significant figures, and we were going to have to round that up because this 8 here is more than halfway to the next number. So our pH will end up being 4.470. All right, so what about the opposite of logarithms, the inverse logarithm? Okay, so the inverse log of, say, 4.37 in this case. Okay, another way to write that is right here, 10 to the 4.37. Okay, so then that's going to give us a number of, 23,442.288. So how many significant figures do we have? Well, we have to know how many significant figures we have in our inverse log value. And again, we're just looking at those 2 numbers right there, right? The mantissa. So the characteristic, the 4 there in blue, does not count as a significant figure. What we end up with is our number with 2 significant figures, right? 2.3. Right? And this 4 here, again, if you look at the 4, you can see that it is just a power of 10. All right, so another example, if we have a pH of 4.37, what is the concentration of H+? So if we have an example again where we're trying to figure out the concentration of H+ given a pH, if you remember from general chemistry, the concentration of H+ equals 10 to the minus pH. Okay, so 10 to the power of minus 4.37. Right, so where are the significant figures in this case? They are right there in the mantissa. So our concentration of H+ is going to be equal to 4.266 times 10 to the minus 5 molar. But again, that's too many significant figures. We only need 2, so we will be rounding that 2 up. So this is going to end up being 4.3 times 10 to the minus 5 molar. Okay, so let's just go through a couple practice questions, and then that'll be it for this. So which of the following represents the answer to the correct number of significant figures? The inverse log of minus 0.494. There is the answer, all the numbers you might see on your calculator. So the question is, how many significant figures does that number have? Okay, pause the video if you need to. Take a second to try and figure this out. So what is controlling the number of significant figures? Remember, if it's an inverse log, this is the characteristic. This is the mantissa. So the mantissa is what is going to be controlling the number of significant figures. So in our value, those are the first 3 significant figures. But of course, we have a number beyond that that is more than halfway to the next number. So the answer in this case is going to be D, 0.321. Okay, another example. Which of the following represents the answer to the correct sig figs? This is a simple multiplication. So remember, multiplication, we are worried about the number that has the fewest number of sig figs. In this case, that is this number here. Right, so this one has 5 sig figs. This number has 7 sig figs. So our final answer should only have 5 significant figures, so 63.602. And once again, that 8 beyond the last sig fig is more than halfway to the next number. So our answer in this case should be, again, D. Okay, so there it is, significant figures. If you have any questions, you know where to find me. Send me an email or visit one of my Zoom sessions. And as always, you will see me in the next video.